Good morning, Alfredo.
Good morning, Joanna.
Thank you for accepting our invitation for the Greener Talks. This is our fourth Greener Talk organized by AXIA Innovation in the context of the Horizon 2020 Greener project. Therefore, I would like to welcome Dr. Alfredo Perez de Mora from TAUW and kindly ask you to introduce yourself.
Yes, thank you. I will maybe have share some slides with you for this talk. So maybe a little intro on myself and also on TAUW, which is the company I work for and is an official partner of the Greener project. So my background is in biological sciences. I did my master in science at the University of Seville in Spain. Continue later in doing also my PhD at the Institute of Environmental Resources and agrobiology in the field of environmental technology. My expertise is mainly in environmental engineering and microbiology, but also on hydrogeology and soil sciences in general. After finishing my PhD from approximately 2006 to 2014, I moved abroad and work in different projects as a scientist and researcher at institutions in Canada, at the University of Toronto, and then at the Helmholtz Center in Munich, Germany. And finally, in 2015, I joined TAUW, my current employer, as a project manager and environmental engineer, working mainly in remediation projects for soil and for contaminated soils and groundwater. As I have mentioned, TAUW is one of the partners of the Greener project. Also a little background on TAUW. TAUW is a company that was founded back in 1928 in the Netherlands. So we had almost 4 years ago our 19th anniversary, and we're heading for one century of history at TAUW. In Europe, we were present in 6 European countries. So we are in Spain, France, the Netherlands, and Belgium, Italy, and Germany. The company has about 1,100 employees, and we have 3 countries that are involved within the Greener project. TAUW Iberia, also representing Spain, TAUW Belgium, and TAUW Germany. Myself, I'm based in Munich, here at the office in Munich. And here you can see some of the services that the company provides, all related to environmental engineering and consulting. Aspects that are probably very interesting for the Greener project are soil and groundwater services, environmental monitoring. We also have our own unit with field technicians that perform work in the field, and also services related to digital services like geographic information systems and also modeling. The company has a strong focus on sustainability. We also have an international sustainability program within the company. And this is one of the reasons also why it is so important for us to be part of European research and innovation projects such as Greener. So with that, I move to the next slide.
Yes, thank you very much for this introduction. We can then start with our first question, indeed. So could you please briefly present the activities that TAUW is leading and supporting under the Greener project?
Yeah, so TAUW's contribution to the Greener project, I have kind of divided this into 5 main aspects. So the first one is a fundamental aspect which is related to the access and sampling of access to contaminated sites and the sampling of contaminated soil, sediment, and water samples, like you can see here. So sediments, groundwater mainly, but also wastewater from industrial facilities, also from hospital. We have TAUW works at at many different sites and has contact with different types of clients. So it's not always easy to get access to these type of sites. And so this has been one of the main tasks or activities that we had at the beginning of the project, providing the materials that the partners can use in the lab, contaminated samples, so that they can test their technologies with those samples. Another important aspect that TAUW brings into the project is related to technology, performance, and upscaling. So what we're doing, or what we have done, is also provide evaluation guidelines and criteria, so that partners can check whether their technology is doing what they expect to do, and whether their technology can be moved into a higher developmental stage. And an important aspect when that happens is how the technology can be scaled up, so that it can be used, for example, for pilot testing, either in the lab at a larger scale, in a large bioreactor, or maybe in the field. So that's a second aspect that I'd like to highlight about TAUW's contribution. As we are in charge, let's say, of many of the sites that are within the GREENER project, we are also responsible for the pilot demonstration for the most promising water remediation technologies. We currently have two pilot tests that are ongoing or are about to start. One is in Belgium, so it's mainly the colleagues at TAUW Belgium that have been in charge of that, and we'll present, or we'll see some results of that pilot study later on in the presentation. And we have and for that pilot, we're also contributing, or we're working together or collaborating with another GREENER partner, the Materials Institute, MANO, also in Belgium. And for the second pilot test is a site located in Tarragona in Spain, and there we're working also with LATAD Institute Center, another GREENER partner, and this one is based on bioelectrochemical systems. And that one will start probably, it's expected to start in June this year. Since we are also working on environmental engineering and consultancy, we have to deal a lot with regulatory and legal aspects of and risk assessment of sites, contaminations, and so on. So we're also supporting task 7.5 of the project that is dealing with this kind of things. And finally, just like every other partner, we try to contribute as much as we can to Working Package 8, which is related to communication and dissemination of the results and activities that we do within TAUW.
Great. Thank you for this, Alfredo, really, and for being here, of course. And we can now pass to the second question. Great. So as you mentioned, TAUW is leading the scale up of the optimal greener technologies. So could you elaborate on the challenges or the drawbacks that you had to face?
Yeah, so there are many challenges, or multiple challenges, that you're faced when you want to transition from what you do in the lab to the field. And you have to think about it like we start with a system where it's very small, both in time and in space, where we have a very controlled environment. And we want to go later on to a much complex situation, right, with a lot of heterogeneities. I have brought an example here just to illustrate this. What you can see here on this image is soil profile going from 0 to down. I think it's about 6 meters below ground. And you can see there are different colors and there are different structures represented here. So we have sometimes to deal in the soil with gravel, which is kind of a rough type of soil with a lot of porosity. We moved then into a fine sand here. It's still also a soil layer that it allows water to move, groundwater to move. And then we have finally here a clay, which is a very fine and condensed material that allows almost water not to circulate. So this is the kind of, this is within just 6 meters of soil, a kind of very common situation that you're faced with, right? That sets up a lot of challenges in terms of the hydraulics of a site, how you can distribute substrates, how you can bring to the microbes that are present in the subsurface the things they need to work, how you can bring the microbes maybe to the areas that need to be remediated, and so on. And of course, it's also challenging to maintain these conditions in the long run, right? As we can see, working in the field is not a matter of just a few weeks, but we're talking here about maybe months, half year, or a year of treatment. So you also need to be able to maintain those conditions in the long run. The way that we work internally at TAUW, but also I think that that's the approach that we have been following within the GREENER project, is we start testing the technologies at a very small scale. So at the microcosm scale, we then move to a little bit of a more complex system. In this case, the way we have done it for the current study is moving into soil columns, where you're able to also have a recirculation of water right through the soil. And then finally, when this treatability testing is successful, we can then move into the field, and we first do pilot testing on a small area. And if the results are successful, then we can think of scale of full implementation at the site.
This was very interesting indeed, and a lot of challenges that you are facing successfully, for sure. So if we move to our last question, regarding the contamination sites that TAUW is leading, if you could present the advancements of work.
Yes, so for today's talk, I'd like to present the advancements on the pilot demonstration at Site 8. It's an industrial metallurgical site located in Belgium, and I have said in the beginning, it's the colleagues from TAUW Belgium, Dirk Paulus and Herwig de Wilde, who have been leading the project there. The idea for this pilot is that we have a metal contamination in groundwater at this particular site. And the idea or the principle of what we want to do of the bioremediation approach is to precipitate the metals that you have soluble in the groundwater as insoluble minerals, as metal sulfides. To illustrate this, I have this picture here where you see a microcosm bottle, and this kind of black precipitate that you can see here are iron sulfide particles or metal sulfide particles that once they form, over time, they tend to precipitate. And this is the kind of thing that we want to reproduce in the field. How we can do that? So the idea in GREENER, we work with microorganisms. So the idea is to biostimulate the activity of native, this means organisms that are already present at the site, native sulfate reducing bacteria in the aquifer. So these bacteria have the ability to transform sulfate into sulfide, and then the sulfide can bind metals and form these metal sulfides that are insoluble and finally precipitate and are removed from the water. The novelty behind this pilot study is that there are very few field scale demonstrations on this type of technology. So the technology, or at least the biological process, is long known, but there are not many experiences at field level. We also have a mixed contamination of various metals and metalloid species. So we have on the one side nickel and zinc. They are cations, they're positively charged in the water. And we have the metalloid arsenic, which is usually present as an anion, as arsenate, and is negatively charged. So they do have different behavior in the soil matrix and in the subsurface. And we also have to deal with an acidic pH. At some points of the site, we have even lower pH than 4 or 5. We are down to 2. And this can be quite challenging for microbial activity because they have an optimum, microorganisms have an optimum pH of activity, and usually if it is very acid, this activity can stop. And finally, why we decided to do this at this particular site is because there is plenty of sulfate in the water at this site. So we have this essential component of the microbial activity in order to steer and also stimulate this process of sulfate reduction and metal precipitation as sulfides. I will move then into the next slide. I have here some pictures on the pilot that started back in May 2021, so last year, and it has been going. There's actually still going as of today, so we're still doing some monitoring. But basically, the results I have are for the last slide are until February 2022. And what you can see here is an image of, it's a map of the site in red. So the red stars are the points, the injection points that where we introduce an organic substrate that can stimulate the microbial activity in the subsurface. And what you see here is on the one side, the injection technology is a special injection technology called spin injection. And you can see here that the you can see that the drilling dig turns around and it can distribute the substrate one at the same time that is penetrating through the soil profile. The substrate is stored in tanks, and from here it is brought with this piping into the subsurface. And we also have, so we have these injection points, as I just mentioned in red, but we also have some monitoring wells, some monitoring locations where we can take groundwater samples and then we can check what is happening, if the microbes are being active or not. We can see if the metals are being removed and precipitated and so on. And finally here, there's another image where you can see how these injection wells or monitoring wells look like. And there are some parts or segments of these wells that are in contact. So they're filtered and they're in contact with the groundwater. And that's the those are the segments from which we can take samples and where we can make observations. And for this particular pilot test, we did injections at 2 depths of the aquifer, 8 and 9 meters below ground level and 10 to 14 meters below ground level. And the target was to distribute the substrate within the sandy layers that are conductive of water. So these layers here are between clay layers that act as aquicluds. That means that they do not transport water. And then I move to the final slide just to show some of the results that we had. What you can see here is 3 graphs showing the evolution of arsenic, nickel, and zinc concentrations over time. So this one is starting actually not in July, but it's in May, and it goes all the way to February 2022. And the 3 curves that you can see in each one of the graphs represents one different location. So we have one well, which is called 1862 in blue. Then we have another monitoring well, 9001 in orange, and finally 9003 in gray. And here are the concentrations of arsenic in micrograms, or the metals in micrograms per liter, are shown over time. And what we saw is that basically for well 9003 in gray, we see no change over time after treatment. For well 9001, we didn't see anything until basically October 2021. And after that time, the concentration of the metals increase. And the interpretation that we have for that is that we had a second injection, so that the 2 injections of substrate we did was at the beginning of the pilot study, and another and just at the beginning of October, just before this point here. And so we think that there was, through the injection, there was a displacement of water, and probably we had a displacement of the contaminated water from this area into that monitoring well. And finally, we saw a very positive and successful response at the well 1862. So here in the beginning, so until October 2021, we saw almost nothing happening, or a very slow kind of response of the metals. Maybe for zinc there was a better effect, but then after the second injection, which happened here, we see a drastic reduction in arsenic, nickel, and zinc concentrations down to non-detectable levels. So we're moving from, let's say, thousands of micrograms per liter to non-detectable levels. So this was the results from well 1862 prove in the long run that actually the treatment that we applied was effective, that we were able to stimulate the native sulfate-reducing bacteria, and therefore that we're now in a position where we can think of a full-scale implementation. We're still doing monitoring, because it is important to check also in the long run that the removal is really stable after some months, and the metals are not being redissolved in the groundwater. And the second thing is we also need to conduct, together with the manual, microbial analysis to see how which microbes were active and were responsible for the activity that we have seen, and for the precipitation of the metals. And with that, I would like to finish the presentation of the results for the pilot testing at Site 8.
Thank you very much, Alfredo, for participating, first of all, in the talk, and for sharing all this interesting information with us. It was a pleasure, and it was very valuable for our greener dissemination campaigns to be here with us. And everyone, stay tuned for more greener talks. Thank you.
Thank you. Bye-bye.
Bye.